Hi, everybody. This is Dr. Nigro with the Chem Calculation screencast. This one's going to look at the solubility product constant, KSP, and some of the information that we can use that constant for to determine things like molar solubility of substances and if precipitation is going to occur in a particular dissolving process. All right, so let's talk about what we mean by the solubility product constant. All right, KSP is an equilibrium constant, similar to Kc or Kp, but it is specific for the dissolving of a solute into a solvent. All right, now for our purposes, we're going to see this mostly in the form of ionic compounds dissolved into water. So the formation of aqueous solutions. But that's not to say it has to be focused only in that particular area. But that's what we're going to use for our examples and the practice problems that we're going to do. All right, so let's start with an ionic solid. So we've got silver sulfate in its solid state, and we're going to try to dissolve it into H2O, right? And when that happens, we're going to yield two ions, the silver ion and the sulfate ion. All right. Now, if you are familiar with the solubility rules, then hopefully you recognize that this is one of our insoluble salts according to those rules. All right. Now, insoluble salts are insoluble for the most part, but usually there is a small portion of them that will dissolve in that solution, just not very much. All right, and that's where our KSP value is going to come in. All right, that value is going to give us an idea of how soluble something is. All right, so if we write our KSP expression for this reaction, it's going to be equal only to the ions. All right. The reason, remember, only aqueous solutions and gases are allowed into your equilibrium expressions. That solid, that silver sulfate that's on the reactant side, cannot go into the expression. All right. So if you look at what this expression tells us, all right, KSP values that are large have lots of ions in solution. All right, whereas KSP values that are, oh my goodness, the spelling today is a little off, are small, have few ions solution. All right, so a substance that's very soluble, let's say sodium chloride. All right, if we were to write out its KSP expression, that number is going to be very large. All right, so we don't tend to look at those in terms of equilibrium because we say that that reaction goes fully to the product side. All right, other insoluble salts do have a state of equilibrium where we've got a little bit that's dissolving at the same time that a little bit of the solid is reforming. So it is moving back and forth between reactants and products, so we can have an equilibrium expression for that. But your KSP values are going to be small. So you're going to get things like 1 times 10 to the negative 10th, 1 times 10 to the negative 14th. I've seen some salts that's 1 times 10 to the negative 38. All right, so these are very small values, which tells us that there is a very small amount of ions that are present in that solution. So KSP values are valuable in that they give us an idea of the degree of solubility of something and allow us to compare solubilities between some of our ionic solids. All right, what else can we use that KSP for? All right, so this is one use, determination of solubility. All right, this is a second use. All right, we can use that value to determine the molar solubility of the compound. All right, what that really means is we can determine the concentration of ions in solution. All right, so we just set up our ice chart and we would use our KSP expression and the KSP value, and we would solve for X. And that X value would in turn be the molar solubility of a particular ion within solution. All right. The third thing that we can do is determine if precipitation will occur. All right, so in this case, we're going to be comparing Q to our KSP value. So this is going to be one of our reaction quotient situations. All right, we saw that with KEQ, a comparison of those two gave us an idea as to whether the reaction would be producing more products to reach equilibrium or producing more reactants to reach equilibrium, or if we were at equilibrium. All right, same thing here. All right, if your Q value is less than your KSP value, then we say that solution is unsaturated. All right, and if it's unsaturated, then more of that solid can dissolve. So we're going to get an increase in our ion concentration. All right, we might do our calculation and find that Q is equal to KSP. That would be a saturated solution, meaning no more of the solid is going to dissolve. And we are at that point where a couple particles of the ions are reforming solid at the exact same time that some of the solid particles are dissolving into the ions. And so it doesn't look like anything is changing, all right? But in fact, we still have those active particles moving back and forth, all right? And then finally, we could calculate Q to be greater than KSP. This would be a super saturated solution, and we know that supersaturated solutions are very unstable. All right, so we're going to get a precipitate form. Whoops. Oh, what happened? Sorry about that. All right, so we need to use that Q value to determine what is happening right at that second, and then compare that to what KSP tells us should be happening if we're at equilibrium. Okay, so again, writing out those expressions, using them first to get an idea of the solubility of that particular salt, and then using the KSP value and the expression to find the actual concentration of our ions, and then finally calculating the reaction quotient to determine whether we're going to have precipitation or not. All right, so I've got a couple example problems that we're going to work our way through. All right, we're going to start with this one. It was experimentally determined at 25 degrees Celsius. Oh, let me go back. I'm going to put a star up here. All right, KSP is temperature dependent. All right, so just like KEQ, KC, KP, you have to list the temperature in the problem, all right, because your KSP value at 25 degrees may not be the same KSP value at 50 degrees. All right, so sorry, I meant to put that on there. It is temperature dependent, so be very careful. All right, we're looking at the solubility of barium sulfate in water, and we've got a density. What is the value of KSP for barium sulfate? All right, so let's start by writing out the dissolving process. BaSO4, solid, equilibrium. We've got barium plus 2 ions and sulfate ions. All right, now if I want to calculate KSP, I need to know these two values. All right, well, it tells us the solubility, all right, which means that this value is the amount of barium and sulfate present in that solution. Because remember, that one barium sulfate unit splits in these two ions. So if I had 0.0009 grams per liter of the barium sulfate, when it splits, I'll 0.009 of the barium ions and 0.009 of the sulfate ions. The problem is that your equilibrium constants, your KSPs, need to be in molar concentrations. All right, so the first thing we need to do is convert. All right, so we got to go from grams to liters to moles per liter. All right, well, the only way to get from grams to moles that I know of is molar mass. All right, so I'm going to have 0.090 grams per 1 liter. And then over here, I'm going to put the gram down here and the mole up here, and that is my molar mass. So I'm going to calculate the molar mass of barium sulfate. All right, and then I'm going to say that 1 mole of that substance equals that mass, which is 233.38 grams. So that's going to let me cancel my grams and leave me with moles per liter, which is my molarity. And this turns out to be 3.90 times 10 to the negative fifth molar. All right, so that means that barium is 3.90 times 10 to the negative fifth molar when dissolved, and the sulfate ion is present at 3.90 times 10 to the negative fifth molar. All right, so now I have the concentrations of my two ions. I can write my KSP expression. It's going to be equal to the concentration of the barium ion times the concentration of the sulfate ion. All right, so that's going to be 3.90 times 10 to the negative fifth times 3.90 times 10 to the negative fifth. So the KSP value for this particular ionic salt or ionic compound is 1.50 times 10 to the negative ninth. All right, no units. All right, that's a pretty low number. So not a whole lot of it is going to dissolve, but a little bit is going to dissolve. All right, let's try our next one. All right, what is the molar solubility of silver chloride in water at 25 degrees? The KSP for silver chloride is 1.6 times 10 to the negative 10th. All right, this time we're going to be looking for the concentration of the ions in solution, so it's kind of the opposite of what we just did. So we should always start out by listing out our process. AgCl solid forms Ag plus 1 ions and Cl minus ions. All right, there's my reaction. I'm going to set up my ice chart. Now, for our ice charts, the initial amount of the salt is going to be irrelevant. I usually just put excess, all right, because not all it's going to dissolve. I mean, that KSP value at 1.6 times 10 to the negative 10th is very small. All right, initially we don't have any of our ions. For the change, minus X, the solid, plus X for each ion, and then we'll still have excess at the end for the solid, and then X and X for my two ions. All right, so for my KSP expression, it's going to be equal to the concentration of silver ions times the concentration of chloride ions. All right, 1.6 times 10 to the negative 10th for that KSP value, X times X for the silver and the chloride, that's X squared. So I'm going to take the square root of both sides, and I'm find that the X is equal to 1.3 times 10 to the negative fifth molar. All right, so this equals the concentration of Ag plus and the concentration of Cl minus. All right, so if I dissolve silver chloride in solution, at most, I'm going to have 1.3 times 10 to the negative fifth molar of each of those ions. All right, number 3. What are the molar concentrations of silver and chromate in a saturated solution of Ag2CrO4? The KSP for silver chromate is 9 times 10 to the negative 12th. Okay, so let's start with our dissolving process. So Ag2CrO4, solid. Oh, I have a lot of silver in this today. 2 Ag plus 1 ions, and then my chromate ion. All right, ICE. Initially excess, 0 and 0, minus X plus 2X plus X. Then I'm going to have excess for that solid in the end, 2X and X for my two ions. Okay, right, and I start with my KSP expression. That's going to be equal to the silver ion squared times the chromate ion. All right, so 9.0 times 10 to the negative 12 is going to be equal to 2x squared times x. All right, so 9.0 times 10 to the negative 12 is going to be equal to 4x cubed. All right, so I divide both sides by 4, and then I take the cubed root, and I find that x is going to be equal to 1.3 times 10 to the negative 4th molar. All right, that seems like a lot. 1.3 times 10 to the negative 4th molar. All right, so if we come over here, that is actually going to equal the concentration of chromate. All right, and then we're going to have 2.6 times 10 to the negative 4th molar for the silver. Okay? All right, I'm going to check. Hold on. I'm going to check that. I'm not positive that that's correct. This happens sometimes too. All right, so we've got 9 to the negative 12. Is that divided by 4? All right, now I'm going to take the cube root of that. No, that's right. All right, I don't know why it seems small. I mean, too big to me, but it does. But the math works out. So we have 1.3 times 10 to the negative 4th molar of chromate in solution, 2.6 times 10 to the negative 4th molar of silver ions in solution if it is saturated. Okay, so now we're going to do one of our precipitate questions. All right, will a precipitate of lead 2 sulfate form when exactly 100 mils of a 0.003 molar lead nitrate solution is mixed with exactly 400 milliliters of a 0.04 molar sodium sulfate solution? The KSP for PbSO4 is 1.3 times 10 to the negative 8. All right, so again, I'm going to start with the dissolution reaction. So PbSO4 solid is going to split into Pb plus 2 ions and sulfate minus 2 ions. All right. Now, we're asked about precipitation. So what we need to figure out is Q. Right? I know what KSP is, so I need to figure out what Q is. So I need to know how much of each of these I have present in solution. And these are coming from that lead nitrate and that sodium sulfate. So I need to use those. So I need to know how much Pb plus 2 is present. So I start with that. Now, I've got 100 milliliters of a solution that's 0.0030 molar. Now, that lead nitrate splits into 1 lead ion and 2 nitrates, but I only care about the lead, and it's 1 to 1. All right, so that's why it's 0.0030 molar lead ions. But I have diluted that, all right, because now it's in a total volume of 500 milliliters. So I need to take that into account. So 500 milliliters M2. All right, so we use our dilution formula to calculate the new molarity of lead ions, and we get 6.0 times 10 to the negative 4th molar. All right, so 6.0 times 10 to the negative 4 molar. All right, and then we need to repeat, but we need to look at the sulfate ion. All right, so we have 400 milliliters of a solution of sodium sulfate. So it's 1 to 1 for the sodium ion and the sodium sulfate. So it's 0.040 molar sulfate. But now we're in 500 milliliters of solution. So what is our new molarity? All right, again, use the dilution formula, and we find that we have 0.0080 molar of the sulfate. All right, so now we set up our Q expression. Q is going to be equal to the concentration of lead ions times the concentration of sulfate ions. And then we're going to plug in 6.0 times 10 to the negative 4 times 0.008. All right, multiply that out, and we get 4.8 times 10 to the negative 6. So Q is 4.8 times 10 to the negative 6. So now we need to compare that to KSP. All right, so KSP is equal to 1.3 times 10 to the negative 8. All right, so Q is greater than KSP, which means we have way too many ions in solution. All right, so this is super saturated. All right, so precipitate will form. All right, so if we poured these two solutions together, we should see solid fall out of solution because that is those excess lead and sulfate ions that cannot still remain in solution. They have to come out of solution because it's super saturated. Okay, all right, so these are just some examples of how we can use the solubility product constant. And remember, it's useful to determine the solubility of a particular salt. Remember, the higher the number, the more soluble it is. The lower the number, the less soluble it is. We can use it to determine the molar solubility. What is the actual concentration of ions in solution for that particular salt? Or we can calculate the reaction quotient and use that Q value in comparison to the KSP to determine whether we have an unsaturated solution, a saturated solution, or a supersaturated solution where we should see precipitation.